analog transmission. So what did I tell you before we ended the digital transmission part? I told you that it is better to send the data in the form of here. Okay, so it is better to send in the form of digital signals, because digital signals have certain advantages. But we also might encounter at times cases where you need to send the digital data as analog signals, right? So that means that the sender has certain data which is digital in the digital form, and that has to be sent through the channel as analog signals, right? So we might also have this kind of cases. Okay, there might be other combinations, as I told you at the outset, that there might be other combinations as well. But so here, for the purpose of this course, we are going to cover only we are going to cover what happened. So we are going to cover only basically sending the digital data as analog signal, right? So analog data as analog signal is possible. Analog data digital data as digital signal. So all these combinations are possible basically, right? So let us now, without losing any further time, let us try to understand that how the digital data will be sent as analog signal. Okay, so for this you need to do some digital to analog conversion, right? So for digital to analog conversion, basically you need to change one of the characteristics of the analog signal based on the information that is there in the digital data. Now this digital data has to be carried over some analog signal, and that analog signal is called the carrier signal. So let me repeat once again what I said. The digital data, like in this particular figure, you see we have a sender, we have a receiver. Now the intent is to send this digital data, which is in the form of zeros and ones. Now this digital data has to be carried over this link, which supports only analog signaling. So it's an analog channel, right? So through this analog channel, we need to send this digital data in a certain way, which finally will be received in the form of the sent digital sequence, digital data sequence. So the digital data needs to be carried on as analog signal, and that analog signal which carries this data, the zeros and ones, is called the carrier signal, carrier analog signal. This carrier analog signal has a certain frequency which we denote as F subscript C. The carrier signal has certain frequency which is denoted as F on subscript C, that performs the functions of transporting that particular digital data, which is in the combination of zeros and ones, in the analog waveform. So this analog waveform is going to kind of encode these zeros and ones inside it, so that these encoded zeros and ones will be carried to the other end, and they have to be decoded, and you get these zeros and ones back. Okay, so let us have a look through how this could be achieved. So if we are talking about sending certain bits, there is a bit rate, like the way we saw the concept of bit rate and baud rate in the last class also, right? In the context of digital signals, we have seen this. So here also, let us try to understand how the bit rate is going to be. So bit rate is denoted as capital N. It is basically the number of bits per second, BPS. So same like what we have encountered in the last class. For digital transmission, we have encountered the same thing. Nothing has changed. Now, we also had encountered earlier something called the baud rate, which is, as per the definition, exactly the same that we had covered in the last class. And let me repeat it once again over here. So the baud rate is basically the number of signal elements per second. It is measured in terms of bauds. So signal element is baud rate. Bit rate is basically bits per second. Signal elements per second is baud rate, and bits per second is. So we have seen before that corresponding to 1 bit, you might have 2 signal elements, right? So that is possible, right? Or there could be the other way around also. So baud rate and bit rate are not the same. That is something that we have to remember. So if we are talking about analog transmission per se of the digital data, the signal or baud rate is less than or equal to the bit rate. And it is going to be measured in this way. S, which is the signal rate or the baud rate, is equal to 1 by Rth n. So n is the bit rate, and 1 by R multiplied to it gives you the signal rate or the baud rate. Now, what is this R? R is the number of data bits per signal element. R is the number of data bits per signal element. Okay. So let us have a look at some numerical problem. So let us say that we are talking about an analog signal that carries 4 bits per signal element. So per signal element, you have 4 bits which are encoded in it. If 1000 signal elements are sent per second, I ask you what will be the bit rate. Simple arithmetic. So you have R equal to 4. Why R equal to 4? R bits per signal element. So R equal to, 4 bits per signal element. So R is equal to 4. S equal to 1000 given. The question is, what is N? Right? So you use the same formula, S equal to N into 1 by R. And from this, you can get N equal to S into R, which will give you 4000 BPS. So corresponding to 1000 baud, we have 4000 BPS bit rate for this particular example. Corresponding to 1000 signal elements per second, we have a data rate which is 4000 BPS. Clear? Let us look at another example. An analog signal has a bit rate of 8000 BPS and a baud rate of 1000 baud. How many data elements are carried by each signal element? And how many signal elements do we need? Again, very simple arithmetic, nothing big deal. So let us quickly, in the interest of time, let us have a look at the solution. But you guys will have to do similar kind of problems at your end to get more familiarized. So in this example, what is N? What is S? S is 1000, N is 8000, and then R and L are unknown. R and L are unknown. So first you have to compute R, right? So you can find, using the formula S equal to N into 1 by R, you can compute R. So R becomes 8 bits per baud, right? So now, so what is going to be the value of L? The same thing that we have discussed earlier. So L is what? L is 2 to the power R. So basically L is 2 to the power R, or R is log L to the base 2. And using this, you get L equal to 256. So 256 levels are going to be introduced. 256 levels. So let us now, with this basic understanding of the relation between bit rate, baud rate, etc., in the case of analog transmission, let us now have a quick look at how the conversion of the digital data can be done to analog signals, and how the digital data can be encoded or converted to the analog form. So I told you that for this we need some analog pulse, right? We need some analog waveform. That waveform will have a frequency f subscript c. That is called the carrier frequency of that analog waveform. Now, there are, with this being made available, you can make this digital to analog conversion in 3 different ways. Number 1, amplitude shift keying, ASK. Number 2, frequency shift keying, FSK. And number 3 is phase shift keying, PSK. There is also something which is quite advanced, which is called quadrature amplitude modulation, QAM, which is kept out of scope from the syllabus of this course. So we are not going to cover QAM over here. So our focus is going to be on ASK, FSK, and PSK. Let us first start with the ASK, which is pretty simple. Right? So let us try to understand what is this ASK. So in ASK, you encode every digital data with a signal with a certain amplitude level. So this carrier signal that we talked about, this carrier analog signal is going to have 2 different amplitudes. One will denote the digital value 1. The other signal level is, the other amplitude level is going to denote the digital data 0. So digital 1 would not affect the signal. You can encode that way, whereas you can encode in such a way that the digital 0 would affect the signal, thereby making it 0. So the line encoding will determine the values of the analog waveform to reflect the digital data being carried. So I will show you how it works, but before I do, I also wanted to introduce to you another thing which is important. So if we are talking about ASK based modulation, right? So modulation is basically, how you make this kind of conversion. So if we are talking about this modulation in the form of ASK, then the bandwidth B of ASK is computed as the product of S, which is the signal rate, times 1 plus D, which is where D is basically a factor introduced due to modulation and filtering. So B equal to product of S and 1 plus D, where D is a factor that gets introduced due to modulation and filtering. Now this factor D lies between the values 0 and 1. So you need to know D basically, or you need to estimate D before you can estimate the required bandwidth. So we will come to it, right? So in ASK, we have 2 levels, two amplitude levels. So these 2 amplitude levels are going to denote 1 or 0. So you have a look at over here. So if we are talking about 1, in this case, you could encode it in a different way also. So here actually, this amplitude level of the signal denotes 1, whereas the 0 amplitude level is encoded as 0. 1, 1, 0. So here you see that per bit you have only one signal element. You have only one signal element. So now you see the values of R is 1, S equal to N, and D equal to 1 plus D times S. And this bandwidth is going to be centered on the frequency of the carrier signal, which is FC. Right? It is going to be evenly distributed in this way. So you have a look once again over here from a different perspective. You have this carrier signal. You have these bits, the digital bits, right? And the bits basically the digital data the digital data. So 10110, and you have this digital data represented in this form. Then you take the carrier signal, then you modulate that carrier signal in this manner to get the modulated signal, which will have 1 encoded this way, 0 encoded this way, 1, 1, 0, and so on. So this is the process using the multiplier, how you can do it. The oscillator circuit is going to give you the carrier signal with the frequency fc, and you take the digital data, you do the multiplication, and then you get this final modulated signal. So let us have a look at some example. So let us say that we have an available bandwidth of 100 kilohertz, which spans from 200 to 300 kilohertz. The question is that what is the carrier frequency and the bit rate if we modulated our signal using ASK? And the value of D is given, it is 1. So you see that the middle of the bandwidth is what? 280 kilohertz, 200 plus 300 by 2. Middle of the bandwidth is going to be 200 plus 300 by 2, 250 kilohertz. So this means that our carrier frequency will be 250 kilohertz. This I told you, right? So this was the figure that I had shown you over here. So this carrier frequency is going to be 200 plus 300 by 2. Okay, that's the entire bandwidth. So by 2 will give you the carrier frequency. So now, so 250 kilohertz. So we can use the formula for bandwidth, which is what? For ASK, it is 1 plus D times S. S is given, D is also given. So D is 1. So 1 plus 1 equal to 2. 2 into S. S equal to N into 1 by R. R is given, right? So R is 1. So because it is ASK, R is 1. So 2 into N into 1, which is going to be 100 kilohertz. So from this, basically, you get N equal to 50 kbps. Right? Now, any question? Any question so far? Oh, it is 11:50 already. So let us go to the next one, which is frequency shift keying, FSK. So in frequency shift keying, so in ASK, amplitude shift keying, what did we do? We took the different amplitude levels to represent either a 1 or a 0. In frequency shift keying, it is basically two different frequencies will represent two different bits. Okay, so for example, right? So for example, if FC is the carrier channel carrier signal frequency, then one frequency is going to be F1 is going to be FC plus delta F, and the other one F2 is going to be FC minus delta F. So you could represent the bit 1 with this particular frequency level, and bit 0 with this particular frequency level, or it could be other way around also, that is perfectly fine. So it is just a representation. So if the difference between these two frequencies is F1, between F1 and F2 is 2 delta F, then the required bandwidth in FSK, over here the formula has changed, right? So earlier it used to be how much? 1 plus D into S, right? So now it is 1 plus D into S plus 2 delta F, 2 delta F. And this basically is shown over here graphically. It is shown over here. So have a look. It is very simple. It is similar to what we have discussed for ASK. So here actually the difference is that we are talking about two different frequencies, F1 and F2. F1 equal to FC plus delta F, and F2 equal to FC minus delta F. So one is going to represent 0, and one of these frequencies is going to represent the bit 0. The other is going to represent the bit 1. Okay, that's the only difference. So that is FSK. So likewise, we have a problem over here. We have the problem reads like this, that we have an available bandwidth of 100 kilohertz, which spans from 200 to 300 kilohertz. What should be the carrier frequency and the bit rate if we modulated our signal by using FSK with D equal to 1? Exactly the same problem as before, but here instead of ASK, we have FSK as the modulation scheme. Same thing, right? The midpoint of the band is at 250 kilohertz. So we choose 2 delta F to be 50 kilohertz. This means that B is going to be how much? 1 plus D into S plus 2 delta F, which is going to be this, right? So from this, basically, you can calculate the value of S and also the value of N. Very simple. Now, coherent and non-coherent FSK. So in a non-coherent FSK scheme, we can change from one frequency to the other. We do not adhere to the current phase of the signal. In coherent FSK, the switch from one frequency signal to the other only occurs at the same phase in the signal, right? So that's the two different types of coherent and non-coherent FSK. There is also something called multi-level FSK, right, which is similar to ASK and FSK, but over here we can use multiple bits per signal element. Multiple bits per signal element. That means that we need to provision our multiple frequencies, each one to represent a group of data bits. Okay, so this is basically how it looks, and the corresponding formula for computing the bandwidth is also given over here, right? So in the interest of time, I am not explaining this further, but it is very similar to what we have discussed so far. Now the other one, which is very, very important, it is called the phase shift keying, PSK. PSK. So here basically the shifting is in the phase. So two different phases are going to represent, so any phase change basically, right? So any phase change is going to signal a particular bit, right? So you see over here, so here we have this particular signal with a certain phase, right, to represent 1. Then you change the phase over here 180 degree, so you get 0. Then again you introduce 1 with the phase as before. The same thing for 1, again the same phase as before. For 0, the phase that was here is considered. So you see the change of the phase basically takes place at these transition points. Here, 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 here there was no change because there were two consecutive bits, the same bits, right? Two consecutive same bits. So in PSK, the bandwidth is computed like in ASK, 1 plus D times S. Okay, and the graphical representation is shown over here, and how this PSK based modulated signal is going to be produced, same like in ASK. So you have an oscillator circuit with the carrier frequency FC being produced of signal and the digital data. So you do a multiplication and you get this one basically, right? So your modulated signal will look like this. The modulated signal is going to look like this. Now this PSK has two parts. One is called the BPSK. The other one is called two types. One is called the BPSK. The other one is called the QPSK. So in BPSK, basically BPSK scheme is quite popularly used. It is used in different communication standards. For example, CDMA, WiMAX, wireless local area network, 11A, 11B, 11G, 11N, satellite communication, cable modems, etc. Right? So this BPSK scheme is used. So here, the modulation, it's a modulation scheme that conveys the data by changing or modulating two different phases of a reference signal, right? So that's the BPSK scheme. Now, so BPSK basically, whatever I had shown you earlier, so that basically, you can think of as the BPSK. Now, so instead of binary, basically you can make the, make 4 different phases to represent 4 different changes in the signal, right? So basically, that is called the quadrature phase shift keying, QPSK. So we do this, we instead of binary, we make it quadrature, in quadrature phases to increase the bit rate, right? And we can code 2 or more bits into one signal element, right? 2 or more bits into one signal element. So now you see that have a look over here, right? Have a look over here. So this is basically how this QPSK scheme basically works. So you have 0, 1, etc., etc. So what you can do is 0, 0, 1, 0, 0, 1, 1, 1. These can all be sent in this manner, right? So in QPSK, basically what we do is we parallelize the bit stream so that every 2 incoming bits are split up and PSK is used as a carrier frequency. So one carrier frequency is going to be shifted 90 degrees from the other, right? So that is why it is called quadrature. So one is going to be shifted 90 degrees from the other. So you see over here the different phases. So this one has 45 degree. This is 135 degree. This is minus 45 degree. This is minus 135 degree. So you have 4 different phases basically, right? So another question, that find the bandwidth for a signal transmitting at 12 Mbps for QPSK. The value of D is 0. The solution is also given over here. So same thing, S equal to N into 1 by R, so which will give you 6 megabaud. And for the value D equal to 0, we have D equal to S equal to 6 megahertz. So constellation diagram, although I have over here, I'm not explaining. I'm just keeping it out of scope, just for making your life a little easier. So what you need to do now, all these schemes, right? ASK, then FSK, then PSK, right? And the two different types of PSK, BPSK and QPSK. These basically you need to really understand the differences between them. Okay, so we are a little ahead of the time, so we'll stop over here. So students, so once again, please make sure that you are basically